Yeah, thank you for the introduction. So this is Braid. So this is work that would not have been possible without my amazing colleagues, John Moeller, Greg Priest-Dorman, Starner, and Ben Carroll. And this is some work we did at the Interaction Lab at Google. So Mark Weiser, in his seminal piece, The Computer for the 21st Century, had this two lines that start the essay. The most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. And it happens to be that this work, both metaphorically as well as literally, is very related to this quote. So with Braid, we propose a new textile architecture that allows us to embed both sensing and display in a compact, flexible, soft form factor that could fit into various types of wearable and portable devices. So what we've seen in recent years is more and more attention to electronics that are more human-friendly, both from a sense of aesthetics, comfort, and ergonomics. But we're also seeing quite a history of using braid and textile, for example, for audio cords and USB cords as a way to relieve mechanical stress or to avoid tangling. In this work, we're specifically emphasizing the opportunity to have this flexibility without requiring a flat or rigid surface. And we're really thinking about ice-free and very scalable sensing and feedback. We also think it's important to try to, as much as possible, preserve the design and aesthetics, as well as the function of these everyday objects that we try to augment. And finally, when it comes to smart fabrics and garments, a lot of the work that's done currently requires the electronics to be integrated from the very beginning. So one great thing about braids and cords is that they often sort of have the loops and the places that you can add them in a post-process. Electronic textiles have also sort of spiked in interest in the HCI community in the past years, even if there's been activity going several decades back in time. But there's a lot of great work happening in the last couple of years, both in terms of enabling technology as well as platforms. And I think it's one great example is tomorrow the RESI paper from the Media Interaction Lab in Austria that I encourage people to attend. And our specific focus in this work is really looking at the opportunity when we're working with a braid and a cord. And similarly, there's been lots of great work in this space that we're inspired by. Papers like Cord Input and Cord UI focus on the design space and how we can augment existing cords with sensing capabilities, and also how they can be used to leverage metaphors with real-world objects, like the ability to decrease the brightness of a lamp by tying a knot on it to sort of limit the flow of current into it. There's a lot of great examples also on sensing, so I was excited to test the TDR system from Wimmer and Bowders live on Sunday to sense absolute position along the length of a string, but also shape tape from Balakrishnan and colleagues. At the bottom, you see a couple of examples that look at really how you can leverage the compactness of a string or a cord to fit it in a very small device. So going back already to 2006 with Blasco's work, basically a string that's embedded in a smartwatch that can greatly expand the interaction space by expanding it in this one dimension, or the retractable strings for various types of badges. So what we have here is one example of a form factor, which is a USB-C headphones design that allows you to tap the cord anywhere on the cord to play pause and to roll it between your fingers to control the volume. So IO Braid's enabling technology is this idea that we use a braiding topology to combine both passive yarns made out of cotton, as well as functional yarns out of conductive yarn, into this braiding topology that we refer to as the helical sensing matrix. So the yarns flow around or spiral around this core in two directions. So there's the Z direction, where you see the yarns labeled from Z0 to Z3. On the other side, we have the yarns in the S direction, also for. And along the length of the cord, they all sort of intersect, spiral around, intersect again, and on and on. So we have this basically a repeated structure where the same sort of intersections return over and over again. In the center, you can imagine that we sort of made a cut through that cylinder and flattened it, so we're seeing sort of the whole thing exposed. And what I've highlighted here is the sensing matrix, so one set of intersections. So since we have 4 plus 4, we end up with 16 intersection points. And to do capacitive sensing, we basically use the classical mutual capacitance. So we have the lines in the S direction working as our transmit electrodes, and the ones on the Z direction as our receive electrodes. So we're basically scanning this little matrix at very high speeds. But obviously it's very low resolution compared to what you would have in your smartphone or touchpad. But the key thing here is really that the matrix repeats along the length of the cord over and over and over again. So that's why I was able to touch anywhere along the length of the cord for interaction. And we'll see, I can see if I can run a live one of live demos. But we're not getting... Okay, cool. Well, I just need to find the prototype to use. Okay. Okay, so here I have the braided cord. And I'm going to zoom out a little bit. It looked good. Okay, there we go. So as I approach, we're basically receiving the amplitude. And you can see the graph in the back, which is basically just plotting the amplitude response. So as I'm pinching or grabbing, we're getting very different actions. And like I said, you can touch anywhere and you get the same response, which is both a feature and a limitation. But remember, again, we're doing this with just 8 conductive lines. Okay. So the other aspect is, of course, well, if we have a matrix, we may be interested in also tracking motion across this matrix. So basically, we want to recover direction. And here we go from just thinking about this as this little touch diamond into a set of columns along the length of the cord, so in different colors here. And the key thing here is that, we don't have access to the columns, we're just dealing with the little matrix. So what we realize here is that by looking in the matrix, every column, because of the repetition, is repeated multiple times, right? So you see the yellow lines sort of extend, but you can basically get the both yellow columns just with these 4 points in the matrix. So now if we extend that with all the intersections in the matrix, we have basically movement across all the columns. And this goes a little bit into detail how we're tracking motion. So if you see the hand that's basically holding the cord, right now touching specifically the green column and a little bit of blue, which would basically give you this type of response. As the braid is rolled between the fingers, it would shift over. So here it's more touching the yellow, and we basically shifted the response along those columns. So if I come back here, so this is basically what gives me this a responsive ability to track rotation with the cord. Thank you. So of course, with any interactive system, we want both input and output. And right now, I just showed you the sensing part. But if you remember, when I talked about the braid structure, we had 24 yarns that are part of it. And we're only using 8 of those for the sensing. So we have 16 still that are passive, just the cotton support structure to give us the textile feel. So what we've done in the next step is to actually replace some of those passive yarns with fiber optics lines. And here you can see what that looks like. So this is just 4 interleaved fiber optics lines that are also spiral around the core that we're now triggering with basically PWM and anti-aliasing to create the illusion of both speed and direction. So sort of taking a step back and looking at what can we do with this from an interaction point of view, we're able to get proximity, contact area, pressure, both relative and continuous, contact time to do things like tapping and long pressing, and the rolling, of course, to do the relative and continuous movement. So we distilled this into sort of like 5 states, you may say, or 5 types of interactions that we enable with our system. So out of reach, the hover, pinching the cord, rolling it clockwise or counterclockwise, and doing a big grab. And those are very clearly distinguishable in the system. So one example here is using a light diffusing fiber for feedback on hover and touch. So as the user approaches the cord, it sort of gradually fades in, and upon touch, we basically switch the color to green. Another example is this directional movement. So as the user is twisting the cord clockwise or counterclockwise, we can similarly generate a motion or a flow. So if you imagine controlling the volume, it could flow up as you're increasing it or flow down as you're decreasing it. So we're thinking mostly about, in this paper, about wearable devices that could sort of integrate and provide you with hands-free access, whether you're stationary or on the move and don't really have the cognitive bandwidth to attend to buttons or other types of controls. But you can also imagine it being a way to control media playback or scrolling through lists. And for the visual feedback, we're thinking both in terms of user feedback on the interactions that are being performed, as well as maybe informing other people about the current state. So I'm listening to music or I'm in a phone call. So a little bit about the braiding. So braiding is this idea of diagonally interweaving 3 or more material strands. So the passive or active yarns or the fibers in this case. And the specific braiding approach here is a tubular maypole braid that is based on an even number of yarns. And the specific braid is a Japanese kumiho braid that has been hand braided with a device called a Maridai stand. We have a range of different architectures that we explored. So I mostly focus on 4x4 because that gives us sort of a good balance between the thickness and the flexibility of the cord, but still with plenty of resolution. And we also have 3x3 that are a little bit more limited. We can use most types of insulated conductive yarns for our technology. So they need to be insulated for the capacitive sensing. But naturally, because of our colleagues in Project Jacquard, we're using their conductive yarns, or one type of yarns that they're providing. This is basically 7 copper tin wires that have been silver coated, bundled together, and then covered with transparent PFA for the insulation. So basically we have 16 of these that form our sensing matrix. The capacitive sensing is provided using Cypress PSOC 4 series architecture. We have the larger evaluation kits that basically just mate with our breakout boards, as well as a smaller PCB that you see next to the coin. And this is what we use for our braided headphones that basically provide this functionality in a standalone form factor. We use a light diffusing fiber from Corning to create this illumination along the length of the cord. This is a glass optical fiber that has scattering nanostructures to leak a little bit of light along the length of the cord. So it's not like a fiber optic that you use for high-speed communication, where you obviously want to contain as much light as possible. And this specific product that we use is from Versalume. It's called Moonlight, and also has integrated phosphor to give us better quality. You can see here again sort of the effects that we're able to achieve. You see the end of the fiber is cut off, so that basically emits the rest of the light. So we get a lot of effect through that. So in future work, we're interested in other braid topologies than this tubular maypole. There's a lot of trade-offs between the textile feel, as well as the sensitivity and robustness. The light diffusing fibers are really great for output, but they're also fragile, so they're a little more sensitive to bending and handling. So we're still working out a little bit of the details how those could be compatible with a more scalable process. And obviously we want to bring also the visual feedback into these standalone form factors such that we can look at this over more longer term to get more interesting data. From a hardware and algorithm standpoint, we're interested in more expressivity, so both in tracking different types of gestures, looking at absolute position. If we're injecting a signal into these, we may also consider bioimpedance to maybe know also who and how they're gripping the cord. And also, like from similar work or previous work, using external sensors or tactile feedback and actuation to further extend these abilities. Lastly, I wanted to mention that we have these development kits, and we are interested in exploring if the community is interested in this. And I think if there's enough interest, maybe we can make a case internally to provide those for research. So I brought a lot of demos from yesterday, so if you want to see this after the talk, you're welcome to come up. So this is iBraid, combined sensing and visual feedback for soft, flexible, and interactive wearable devices. And the last comment is that we have a couple of job openings, so both for internships and full-time positions, so please feel free to reach out if you're interested in that. Thank you.
Yeah, very impressive work. Can I get one of the development kits? Can I get one of the development kits?
I'll put you in the list.
All right, I see a question there.
Okay. My name is Fukumoto from MSR. Thank you for your very cool talk. And I have two questions. The question one is, does it can detect the multiple function? For example, just pinch and just roll, and pinch and roll, pinch with roll.
Oh, good question. Yeah. So why don't we go to the evidence? So here I'm pinching it, and
I think we need the projection back. Can we get the?
Can we get the projection back? I will show it, but
Yeah.
basically yes.
Okay.
And,
Okay. And the second question is if the multiple and the function for the rolling. If we roll the clockwise to the position A, and also okay, first one.
Yeah. Okay. So.
Okay. Roll, pinch, and pinch with roll.
Yeah. So pinch, roll.
And pinch with roll, yeah.
Yeah, you have to try it. So basically, I'm pinching hard right now, and I'm rolling at the same time. Or I can pinch
just rolling.
and just rolling.
I think this sounds like
Okay.
something, we will
Okay,
have our
thank you.
personal demo session here.
Okay.
Maybe you can just give it a try.
Okay, and the second question is if the rotating the clockwise at the position A, the counterclockwise on the position B, what's happened?
Yeah, so that's a great question. So like I mentioned, we have very little resolution, so really dependent on the redundancy. So we can't have multiple touch points because we think that that's the same low touch matrix. So this is not a multi-touch system because of the limited resolution right now. But with technologies like the TDR, you can get the absolute positioning and maybe use that to disambiguate what's going on in that matrix.
Okay, thank you.
All right, I think we are already 5 minutes over, so I would say please come to the front. There are lots of cool demos here, and give everybody who was speaking in the session a big round of applause.